All right, good evening, Charmaine.
Evening, I'm just getting my stuff together. Trying to see.
All right, I can't hear you. Can you hear me?
You're hearing me? Hello?
I'm still not hearing. I'm not hearing you. Can you hear me?
Yeah.
I said that your microphone is open, but it's not hearing you. Can you hear me?
Yes, I can.
Okay. Okay, I can hear you now. I can hear you now. Oh, I'm not sure why I wasn't hearing, but now I'm hearing you.
Hold on a minute. Give me a minute. Let me check something. Yes, Ronaldo, I'm back.
Great. All right. So, as you know, for the finals, we have 3 more topics to cover. We're going to cover 2 of them today. All right.
Okay.
So because they're really short. It's really, really, really short. So sampling distribution is really short and confidence interval is really short. Now, the next one is proportions and hypothesis testing.
Okay.
We'll do that next week. I also got some, so next week, also I got the last year paper. So what we'll do as well is after we finish, all the contents will go through last year paper and then you realize the finals, nice. All right?
Okay, that's great.
All right. So with that being said, we're going to start. The most important thing though is that we want to understand because majority of the finals will come from the last 3 topics. As you know, the finals is everything, but 60% of the paper is going to be on stuff we're about to do now because
Okay.
we've already tested most of the other stuff in the first 2 midterms. So 40% of the paper will be from previous topics and 60% will be on topics that we're about to do now. All right?
Okay.
This is fair enough. So next thing we're going to talk about now after normal distribution is sampling distribution. Sampling distribution, it is really an extension of normal distribution. It is an extension of normal distribution, literally. So of course, in an ideal sense, anytime we go out into a field and we want to obtain some information, right? We're not going to get information from all of our intended audience. We're only going to get information from a portion of our intended audience, just a sample size. So we're going to get statistics. All right. So of course, so far we've been looking at normal distribution and we don't mention nothing about the sample size. So all sampling distribution they know is involve the sample size. Literally, that's all.
Okay.
That's all. All right.
Okay.
So all this bag of chatting right here is putting all of that. Everything that I just said is in this bag of chatting right here. But you know, doesn't matter. So right here, just to look at a quick example to understand this idea of sampling distribution. For example, if a random sample of n equal 3 selected without replacement from a population of 5. Let's say we're choosing 3 random numbers from a population of 5 numbers in total, right? So this is our sample size right here. Find the sampling distribution for the sample mean. Sample mean mean the mean of those 3 numbers that you select. So you realize that, well, if these are the 5 numbers and we're going to choose 3 from it, we remember we already know the formula 5. It would be 5 choosing, how much are we choosing from the 5? 3.
3.
So it would be 5 choose 3, and when you put 5 choose 3 in your calculator, you get 10. So that means there are 10 possible random samples we can draw. So we list out all the 10 possible samples. We could draw the 3, 6, and the 9, or the 3, 6, and the 12, or the 3, 6, and the 15, or the 3, 9, and the 12, or the 3, 9, and the 15, or the 3, 12, and the 15, and it continues. Once you select the 3 numbers that you are drawn, we could then average it and find the mean. So we could find the mean of the 3 numbers. So the sample mean here is 6, sample mean 7, sample mean 8, sample mean 8, sample mean 9, sample mean 10, sample mean 9, sample mean 10, sample mean 11, sample mean 12. Now, of course, when we were looking at normal distribution, a question probably would have asked, what's the probability that the sample mean is greater than 8? Or what's the probability the sample mean is about 10? So of course, to involve the probability now, look at it. There are 10 possible options from this sample that we chose from the 10. And the probability that the mean, the sample mean would be 6, would be just 1 out of 10. Notice it only happened 1 time out of our 10 possibility. 8 happened 2 times.
2 times.
9 happened
2 times.
10 happened
2 times.
Good. 11 happened
1.
And 12 happened
1.
Good. So in that case right there, that right there gives us our sampling distribution. So this table give us now our probability distribution table, or the sampling distribution table. We could go ahead and just put it graphically. Putting it graphically, this is how it happened. Notice that the sampling distribution almost resembles what? The normal distribution, don't it?
Yeah.
This random sample almost represents the normal distribution. Almost represented, yeah. So that's where the whole idea stemmed from. The only difference between sample distribution now, as we say, and normal distribution is when we were looking at normal distribution last time, we were not taking into consideration the sample size. We didn't take into account the sample size, but we have to take into account the sample size because ideally speaking, when we're actually doing these things in the real field, in real world scenario, it's not gonna just be an ideal situation where, you know, we just work out probability. Of course, we have to work out probability based on our sample size. Make sense?
Yes.
So now this is where we're gonna learn now the central limit theory for sampling distribution. So this is the central limit theory now. You don't need to know that they call it central limit theory. That's just the theory. It says if a random sample of an observation are drawn from a non-normal population, meaning it not even distributed normally, but it have a finite mean, mu, and a finite variance, sigma square, Then once the sample size is large, meaning n is greater than or equal to 30, then the sampling distribution is going to be normally distributed with mean mu and variance sigma square over n. So the only difference is normally we'd write regular normal distribution is x follows a normal distribution with mean mu and variance sigma square. No, it's not just x anymore. So Charmaine, it's not just x anymore, it is now bar x. It's now bar x, meaning the sample distributions follows a normal distribution with mean mu, and the variance is now sigma square over n. Cool? So all we do is just divide the variance by n. Cool?
Okay.
Because now we're including the sample size. So I want you to write that down, that first one, because when you write it, it sticks.
Okay.
You wrote it down?
Yes.
All right, great. All right, so now the distribution of the sample mean, that's what we're going to talk about now, which is the formula now for finding the mean. Now, since we look at a new formula for the mean and the variance, let's see how that affects our calculation.
So this form is what? This formula, the formula that you just gave me, it was a central limit theory?
This is central limit theory, yes. This is what we're using for sampling distributions.
Okay.
So no longer just using normal distribution. So remember, you know, we're no longer using normal distribution,
right.
using sampling distributions. Normal distribution was to just warm us up to get us the sampling distribution, because in real life, you're going to have a sample. It's not going to just be infinite number n. It has to be for a sample. You go into a classroom, maybe the sample size is 20 students. Outside of the classroom, you're at a workplace, maybe the sample size is 28, 38. We don't know, but n must be some number. So it can't just be regular normal distribution. But the beautiful thing is that the mean is not affected. So the mean for the sample distribution, so notice it says mu bar x, meaning the mean for the sample distribution remains the same as the mean for the normal distribution. However, now, the standard deviation for the sample distribution, I want you to take this down. The standard deviation of the sample distribution is equal to the standard deviation given for the normal distribution divided by the square root of the sample size n.
Go again, the standard.
So the standard deviation of the sampling distribution is equal to the standard deviation of the normal distribution divided by the square root of the sample size. That's what this formula is saying.
Okay.
This is also commonly called standard error on bar X. Why am I highlighting that? I make sure to highlight it because, of course, you know, when you go into exam, they always gonna put a one question to say who read them notes. So if you look on the midterm packet, the final packet, I underline the questions that we'll do from the final packet. They always tend to ask something involving the standard error. Let me see if I underline one with it. So I just wanted to see how important knowing that they call it standard error is.
Okay.
19, no, 20, no, 21. That's regular confidence interval. All right, I won't get back to it. We'll see it anyways. We're gonna do that anyways. Yeah, but it's very important that you know that we call that the standard error on bar X.
And this is the distribution formula?
Yes. All right, for the sampling distribution. All right, so as we say now, this is just the summary of it. If the variable X follows a normal distribution, with mean mu and variance sigma square, then this is what we use. This is what we're going to be using. Then bar X, meaning the sample mean, will follow a normal distribution with mean mu and variance sigma square over n. That's what we will use from now on. All right?
Oh, this formula.
This formula, yes.
But it's the same one you gave me at the top.
Same one, yeah.
This
Just
is the
a
first,
summary.
the sampling
It's just
distribution.
a summary,
Okay.
yeah. It's just a summary. After all the notes, of course, we have to summarize it. And then, that's why it says remark here. Cool?
Okay.
So let's look at this question together. It says, let me copy it. Copy and go. So, blank page here. All right, so here's this now. Hear what this question says. It says, at UA, the scores of a test can be modeled by a normal distribution with mean score 52 and a standard deviation of 18. So let's say we call the test scores X. So then tell us X follows a normal distribution with mean 52. That's the average grade. And they tell us that the standard deviation is 18. So the variance is 18 square, right?
Right.
Now we don't care about this anymore. We care about we care now about bar X, the sample that we're actually using from. So now they say 5 students are chosen at random. So in that case, we're going to use
the sample.
bar X. So step 2 now, we're going to say now bar X follows a normal distribution of mean 52. And remember, it's variance 18 square over n. And n in this case, they tell us that it's 5 students. So n is now 5.
Right, which is a sample.
Which is the sample size, yes.
Right.
So now we have our sample size. 5 students chosen at random. Now it makes more sense because last time we were doing normal distribution, they just tell us find probability and don't give us the sample size. So that's in idealistic perspective. But now that we have a sample size, now it makes more sense. So now we can go ahead and do this now. So find the probability that the mean is less than 45. So they're asking us to find the probability. The mean scores, remember, is bar X. So they're asking us to find the probability it is less than 45. So first thing is we're going to have to standardize it. We're going to have to standardize it. But remember that when we standardize it now, it is now, this is our, remember, Z is equal to X minus the mean over the standard deviation. But remember that the mean, the formula that we're using for the mean is the mean for the sampling distribution, and the sigma we're using is for the sampling distribution. So in this case now, remember that this one down here is given by, to find this sigma X right here, it's now bar X minus the mean over sigma over the square root of n. That's sigma X, right?
Hold on. Okay.
So just to go back to it, remember we wrote it around. Let me show you.
You wrote it around here, so yeah.
Good. So now we can go ahead.
Formula.
Yes. So now we can go ahead and standardize this. So we'll standardize bar X, it becomes Z is less than, the 45 is our bar X here, 45 minus the mean, 52, divided by sigma. The standard deviation given was 18 divided by the square root of n, but n is 5. So now we just need to work this out. So put that in your calculator. So let's put all of that in our calculator one time. You
45.
have a calculator, yeah, your calculator can put in the fraction just like that, right?
Right, yeah. 45
Yeah.
minus 52 divided by 18.
So when you're putting it in, I want you to make sure you put it, you press the fraction button in the denominator again. So make sure you put a bracket and press the fraction button
I
again.
have 48 and not 45.
Oh, it's 45, thank you. I didn't realize, 45. So when you're gonna put it in the bracket, I want you to make sure you put 18 over square root 5 and you bracket it in the denominator.
Oh, so you put the bracket first, put
Yeah.
the bracket first, and then a fraction button again. Oh, and then you say 18 over, put the square root, and put 5,
Yeah,
and go up and close the bracket, and equal.
yeah, how much you got?
Negative 7. Oh, we get
This is
negative
what you got?
0. No, negative. Oh, yeah, that's what I got. And then I press the
SD, good.
right. That's what I got. What you have there.
Very good. So now we get that this works out to be the probability Z is less than negative 0.8. Let's go with 87. All right, rounding off because we're going to go for a table. Now, this is what we have, but remember the probability Z is less than this negative number, right? The probability Z is less than that negative number. We don't want a negative, so that's just 1 minus the probability.
Right.
Z is less than 0.87.
So look in the table for it now.
So now we're going to the table.
Oh, the table.
Let me pull up the table again, but you should have your printed copy.
I have my printed copy. I'm looking for it.
So go and look for 0.87 and tell me what is that.
0.87. 0.87. 0. No. 0.878. That's what you
Very
got?
good. 0.878, yes. So now we just finish it. It's 1 minus 0.87. What was it?
878.
0.878.
No, man. 80.
80.
0.878. 0.878.
This?
Mm-hmm.
Good. So now we subtract that from 1. So 1 minus 0.8078.
8078. Subtract that. 1 minus 0.0878 equal 0.1922.
Yes, 0.1922, exactly. Very good. So that would be the probability that a student at UWI, from those 5, remember it's from the 5. So that's the probability that a student from the 5 selected would have a score less than 45. So close to a 20% chance, meaning at least one person out of them 5 there definitely gonna average less than 45. One out of them 5 students there.
Okay.
All right, so that's what that is saying. So that is how we use sampling distribution. And there's nothing more to this topic except that we're going to look at proportions after. So imagine this is all the topic entails. It's just to do some questions with it now.
That's it?
That's it. That's why we're going to do 2 topics together today. Yeah, that's it.
How do you identify like a sampling distribution? What are the key terms?
The key term to look out for now is N. If they don't give you an N, it's regular normal distribution.
Oh, it's a 5 students are chosen random, so that would be the
Once
N.
the 5 students, N. First thing for pop up, 10 students, oh, sample, boom, sampling distribution. All right, so that's the key. So I'm glad you asked it though, which we'll touch on. There are some key terms to let us know which topic the question is coming from. So that's that. So you're going to walk me through one more of my examples before we go to the problem set. Then we'll go to the papers. So not looking at this because this is Econ 1005 notes when I would have been doing it. But as you realize, Poisson distribution is no longer on the syllabus. They actually take it off. So we can ignore this.
Hold on 1 minute. Hold on 1 minute.
Yeah, this is actually UE notes. I'm going to email this to you as well. Don't worry.
Go back to the question that we did.
Oh, here it, oh, go back to the working out of it.
No, man, just the question I want to see.
This one?
Just a question. You go back to the blank page. I don't want to see working, the one there before.
Go back to just the questions.
Right.
This one?
Yes. All right. Okay.
All right, cool. All right, so we can ignore the next one because as I said, this is no longer on the curriculum. They take off Poisson distribution. I don't know why they took it off, but it's no longer on it. So let's move to this one. So this one right here, it can be a little bit challenging. So this is what I want you to be aware of. Sometimes now, remember we did this? We did what we call normal approximation to binomial. You remember that?
Right.
So sometimes a question might come like this. The mean of 30 observation of the random variable R is bar R, where R is a binomial distribution with 30 observations and the probability of success is 0.35. State the distribution of bar R. So a question like this now might come and I'm telling you that 3/4 of persons gonna see a question like this and say, Jesus Christ. When what they should be saying is, thank you, Lord, this is easy.
Okay.
All right. So this is the thing now. So we have to remember some stuff about binomial distribution, that the expected value of X is equal to N times P.
Right.
The expected value is the mean mu. So what we're saying then is N times P is going to be 30 times 0.35. So we can work that out. 30 times 0.35, work that out for me.
30 times 0.35. 10.5.
10.5.
5.
10.5. Thank you. Then the next thing we can work out now is the variance of X. Now the variance of X is NPQ. That's for binomial, right?
Right.
So it's going to be 30 times 0.35 times. What is Q?
0.65.
Very good. You're absolutely correct. Say it with more confidence, man. 0.65. Yeah.
Okay.
So now we just work that out. That will be our variance.
Oh, let me work it out now. So it's 30 times 0.35 times 0.65. 6.825.
6.825.
Right.
Good. Now, when you get this now, remember that once it's a sample, it's always, once it's sampling distribution, it's always following a normal distribution. So now we can tell them bar R follows a normal distribution with mean. We work out the mean for the binomial, which is our mean. 10.5, comma, remember that for sample distribution, it is sigma square over root n. In other words, it's the variance 6.825 over n, and n was 30. That's our distribution for bar R.
Hold on, let me get that again.
So remember what we said around in the notes. We said if
Oh, yes.
if X follows a normal distribution with
Right.
mean and sigma square, then bar X gonna follow normal with mean mu and variance sigma square over n. So what we did was work out our sigma square here. Then we divide it by the n, which is 30. We work out our mean, 10.5. That's all we do. Cool?
Okay.
Nice.
Mhm.
And then after that, now it wants us to find out the probability bar R is less than 5. So first we have to standardize it again. So it becomes Z is less than. This is now 5 minus our mean, 10.5, divided by sigma.
Which is 30. No.
Sigma over root n. What is sigma? Sigma is a standard deviation. What's your standard? When you have your variance, what's your standard deviation?
Is it 10? No.
If this is a variance, how would we get our standard deviation?
Square it.
Square it or square root it? Square
Right.
root it. So now we can say that we square root our 6.825. They will divide it by the square root of n.
And n is 30.
30, yes. Now you see when you have square root over square root, this is a law of indices that we need to remember. We can just write one square root there. We don't want to write square root 2 times in our calculator, so we just do this and put one square root. All right, so what we're saying is the square root of A over the square root of B is just the square root of A over B.
Okay.
All right, so we'll just put one square root.
Okay. Hold on, so put this in a calculator now.
Yeah.
5 minus 10.5. Then square root. Yeah, the square root. Square root of 6.825. And then you go. Oh, you go down to the next part. Just go down the bottom and put 30.
Over 30.
Is it? No, what you're going to put? So after you put the 6.825, what you do next?
Oh, did you have it? You press the fraction button?
Yes, and I have 5 minus 10.5.
Oh, remember when you have your fraction button, right? You press the square root here first, then press the fraction inside the square root.
Oh, okay.
Yeah.
And you put in, okay. 6.825 and then 30 equal. I get a negative figure. Negative 11.53. 11.5311.
So negative 11.5311. Now let me check that again because that's a big number. Let me check it again. Negative 11, something off here. All right, and we didn't, let me just put the brackets because something look way off.
All right, so clear it and use the brackets.
Well, you don't necessarily need to clear it. Our calculators are smart. 30 times 0.35 times 0.65, 6.825, that's our variance.
I get error now. When I use the bracket, I get error. All right, go again.
Yeah, it's correct. It's correct. It's definitely correct. All right, no problem.
It's 11.25, right?
Yeah, 11.5, negative 11.5, that's fine. What that means is that basically this is impossible then. Basically, that's what it's saying. So this right here, what we're going to end up get, this is now saying 1 minus the probability Z is less than 11.53.
So when you
That will be 1 minus, well, 11.53. If you go to your normal table, the normal table don't even have that far. The normal table stop at 3.4. Right? So roughly 11 is approximately 1. It's approximately
Okay.
1. It is approximately 1. So what we're saying is that this is approximately 0.
Okay.
In other words, we're saying that the mean will never be less than 5, or it is almost impossible to be 5. It's almost impossible.
Okay.
All right? So it's almost impossible to be 5. Less than 5. That's what this is saying. No problem, that's fine. Which makes sense. If the mean is 10.5, then of the 30 observation, majority are going to bungle up between maybe about 7 to 14. Not just for each 5, the mean.
Okay.
Cool? So that's all that is saying. All right, so with that being said now, before we go to sample proportions, which we'll have to look at now, let's look at some questions just like this from your problem papers now, problem set. All right, trust me, the problem sets are the key to do them. So you're gonna walk me through it now. So I'm just gonna copy this entire question. You're gonna walk me through it. So you're gonna walk me and you through it. So I copied the first one.
So
Here. This is from the problem paper, the problem set. Problem set 8.
Okay.
Problem set 8. It's good to do all of these problem set questions. So this is it now. So it's from problem set 8, sampling distributions. So let us go. It says right here, a well-known resort on the North Coast charges on average $200 daily for lodging costs and meals. Just for lodging costs and meals in a
Lodging and meals.
That's $200. Basically, don't ever go to that North Coast resort. And it says now, assume the standard deviation of such cost is $20. Find the probability that a random sample of 50 visitors to the resort had an average daily cost greater than 200, less than 190, between 190 and 200. Now, Charmaine, I'm telling you that half of the people them doing stats right now are going to see a question like this in the finals. Use regular normal distribution. The regular normal distribution answer going beyond the paper. They're going to ignore the N, and then they're going to come out and say, me get that right, then find out they don't get it right. So I'm telling you that this is how we're going to have to differentiate normal distribution from sample distribution. To differentiate it, what's the key thing we have to look out for?
And it's the sample side, which is 50.
Very good. You have to, once
Yeah.
it's the N given, just throw away regular normal distribution. It's now sampling distribution.
Yeah.
So that's a key thing to identify. So which letter you want to use to just represent the cost of everything that's going on? Which letter you want to use?
A.
A. All right. So A follows a normal distribution. But let's say bar A now. So bar A, the average, follows a normal distribution with mean. What was the mean?
Mean, don't tell me. 200.
Good, 200. Wait, give me a second, I lost access to right. 200, comma,
Yeah. Yeah.
comma what now?
Hold on. 20.
20? 20?
Yeah.
20 square.
20 square. Yes. Sorry,
Over
20 square.
20 square over what?
It is a sample size 50.
Over 50. Very good. Nice. So now the question what the probability that the average daily cost is greater than 200. So on the probability bar A is greater than 200. So we need to standardize it. Standardize it for me. So get.
Hold on. I'm writing it down.
Okay.
So when you standardize it, you get 200.
First thing is when you standardize bar A, which letter this become?
Z.
Z. So you have to tell me the Z first. Greater than 200.
Minus
200 minus how much?
50.
50. We're not
No.
subtracting in.
Hold on. Let me read it again. Measuring cost. 200 minus 20.
20. What wouldn't subtract the standard deviation?
It's just like 200 the cost, measuring cost, and we assume that the standard deviation is 20. Find the probability and if it's 50 greater than this to average daily cost greater than 200. So if it's greater than 200, it's maybe 200 or more. No.
So subtracting 200, you know. See the mean here?
Yeah.
Yeah, so it's 200 minus 200.
It just kind of look impossible today.
Yeah, nothing is wrong in that case. Over what now?
The N, which is 50.
Over sigma bar X. Where sigma bar X is what?
Is it the 20 square?
20 divided by the square root
Yeah.
of 50. It's a standard deviation over the square root of 10. Remember that's the formula, please. It's now your standard deviation of the normal distribution over the square root of the sample size. That's the second thing that we said today, right?
Right.
Have to remember it. But we know 200 minus 200 is 0. Anything over 0 is 0. So we want the probability Z is greater than 0, which is 1 minus the probability Z is less than 0. But even without using the table, we should know that the probability less than 0 is a half.
Right.
1 minus 0.5, which is 0.5. So there's a 50% chance that the cost will be greater than 200. So imagine that that's just, basically if you go to the result, there's a 50% chance your expense greater than 200 for the day. Remember, that's just for the day. What a result. That is That's top quality resort. But let's go now. It says now, part B, less than 190. So what are we working on for part B?
So you're going to standardize it same way.
Write down what, tell me what to write first with part B. Less than 190.
And the probability that A less than 190 is equal to the probability that Z is greater than,
Greater than, oh, it turned greater than.
sorry, less than 190 minus 200
Very good.
divided by 20 square root of 50.
Very good. So punch that into our calculator.
Hold on. Put in this again. Where is it now? 190.
Remember to press your fraction button again in the denominator.
Right. And then put it into minus 20.
How much you get?
Negative 3.53.
Very good. Negative 3.53. So in that case, that is just 1 minus the probability Z is less than 3.53. And that works out to be 3.53. Let's go to our normal table.
Hold on. I'm writing it down.
Okay.
No, go back to the, go back to the working out. .53 in the normal table.
Yeah, well, I don't think my table that I am using has up to 4.41. So I don't think yours has up to 4.41.
No, it's 3.4.
Yeah, I know yours stop at 3.4. So typically they wouldn't give this on an actual test because yours stop up to 3.4.
It's just a practice then.
Yeah, it's just a practice. So I will tell you the exact one for 3.53. So for 3.53, it is 0.99987.
So that's like 5 digits?
Yeah, 5 digits.
It's a 1.3 to the 4th power.
So 1.3 times 10 to the minus 4.
Yeah.
That's what they're giving. In other words, they're telling you that is 0 to the minus 4. So it's 1, 2, 3, 1, 3. That's what we get. So it's 0.00013. Basically, there's almost a no chance that your expense will be less than 190. Imagine that, you know, basically, there is no chance that out of 50 visitors, your money gone less than 190. Let's say that one more time for the result. Basically, there's 0% chance the expense is less than 190.
Yeah.
I just see the numbers differently. How can you go to a resort knowing that there's no chance they're gonna spend less than 190 for the day?
Yeah, but then the question did tell you that, you know, it said charges on an average of $200 daily.
Yeah.
That's
crazy. That's crazy. Basically, no chance you're gonna spend a little bit of money there for the day. 190. That's just for one day. And most time you go on a resort, maybe you go with your family.
Mhm.
You're gonna spend 3 days. It's Easter now, you might spend 3 days. That's $600 for 3 days. Let's convert it. That's 98,000 Jamaican dollars for
For
3 days.
1 day.
For
And that's
3
one
days.
person.
For one person for 3 days. That is not logical at all.
Could be logical for the rich.
$98,000 for 3 days. That's not logical.
Well, not logical for me and you. But what about the person
Great. Okay.
who have it to
Fair enough.
spend?
Fair enough. All right. So part C. So part C right here now, it says, let me see. Between 190,
190 and 200.
the between now, how set up between?
The probability that A is greater than or equal to, I said that?
Greater than 190.
Or equal to 200 and A is equal to 200.
Less than
200. Oh,
That's the between. Good. So now we need to standardize both sides, right?
right.
Now, because we already did standardize those numbers, we don't need to do it again. Remember, we standardized the 190 around here.
And
we got-
190
we got the
was
3.5.
0.000001.
Oh, no, we got,
Okay.
when we standardize it, we got the negative 3.53.
Oh, yes.
And we standardize the 200, we got 0. So we don't need to stress ourselves. We already have those values. So then we have to remember it becomes phi of 0 minus phi of negative 3.53.
You know that they don't
Right.
use phi, they don't use phi when they're teaching.
Repeat.
They don't use phi. What you do is some about at 0.5, something like that you say. I don't listen to our lecture anymore. I don't.
At 0.5.
Yes, to both sides. Yeah, she don't teach it like you. She don't. So when I was listening to one of the packets that you had, like one of the tutorials.
Yeah.
And where you have 5, you don't put that. You have like plus 0.5 or had 0.5. That's what you have. And I was getting confused. So I just went back to your one because I didn't understand what she was saying.
All right, no.
0.5.
All right, no, the only reason why I'm thinking she would add 0.5 is maybe she was looking at the continuity spectrum, which we'll get to in the next.
No,
We'll
but
look
it's
at
the
proportion.
same question.
Oh, it's the same one?
No,
Oh,
you
wait,
don't
oh, wait.
understand.
Oh, I get what you're
Before, you were
saying.
using 5. She wasn't using 5.
Okay, I get what you're saying now. She
Because I
don't
didn't
use
listen.
5.
I didn't look at this lecture. I didn't look at it
Okay.
because it is confusing.
Okay, I understand. Yeah, so she don't use 5. So she do it a different way, that's fine.
No, she add 0.5.
All right, no problem. So now we realize that, but wait a second, we have phi of a negative number. So we know
Minus
we have
1.
to, very good, we have to write 1 minus phi of the positive of the number.
Mhm.
And we already know the numbers. We said phi of 0 was 0.5 minus in bracket 1 minus phi of 3.53. That was 0.9987. And then we work this out. So 0.5 minus 1 minus this. Put all of that in a calculator. Make sure to use the brackets.
So it's bracket 0.
Oh, remember it's 3 nines here. 99987.
Yeah. Minus. Brackets 1 minus 0.9987. Okay, 0.4987.
Very good. That's good. 0.49. How much?
87.
0.49987. Good.
No, 0.4987. Take out one of the 9.
Did you put in the 3 nines?
Yeah. Let me go again. Let me go again. Open bracket. 0.5 minus 0.99987. I'm getting something wrong. I get 6.5.
Oh, did you close the bracket?
Yeah, I
You
did.
open and
All
try
right.
it again.
I
Try it
open the
again.
bracket for 0.5. Then I add another bracket. And I said 1.
Oh, at 0.5, you don't need any bracket out here. The bracket start right here.
All right, then. So 0.5. Open
Minus, put a
minus,
bracket.
yeah, 0.99987. Close the bracket equal. It still give me that. 6.5 times 10 to
Wait, you put it in this way?
the. See, we have it.
0.5
0.5.
minus, open
Oh,
bracket.
I didn't have the minus sign before. 1 point. I didn't have the minus sign. 0.99987. Close the bracket equal. Yes.
Okay, great. All right, so that's that. That is that. Nice. All right, so now that takes care pretty much of this, but we're gonna do one more because I want it to be fluent for you. The more practice is the better. So we'll do the next tutorial question 2. Finally, them not talk about a baby question. Usually they always say something about baby and it's always food or baby. So at least now they're going to electricity. Makes sense now.
Remember them hungry.
Yeah, something that we want to, you know, start to look at. So now they're finally talking about something a little more interesting or a little more intriguing now. They're talking about the electricity. So let's hear what they say. They tell us that the amount of electricity in kilowatt hours consumed per month by a residential utility customer X follows a normal distribution N with a mean of 900, and they tell us that the variance is 110. Data is also collected from a random sample of 25 persons. A, find the probability that the residential utility customer consumes less than 850 kilowatt hours of energy per month, and find the probability that the sample average is less than 840 kilowatt hours per month.
So we are going to say X. We're going to use X.
Yes, X. Now I like this question. I want to see if you catch it. X
X for normal distribution.
Yeah.
Of 900. Comma.
$900, comma.
110 square.
No, just 110. Just 110. This is for X. Now,
Okay.
bar X is what you're talking about.
Yeah.
So bar X would be normal distribution with 900, comma. 110 over
25.
Good. That's for bar X. Please always remember that's for bar X. That is for bar X.
So we know it's bar X.
All right. How you know bar X? Very good question. I want you to observe what we've been talking about so far. Sample average is bar X. Always sample average. Notice that the question then before, I'm going to go back even to these questions you were doing. Notice the bar up on top of it, sample average. Even when they don't tell you, even when they don't tell you, let me look at another one. We zoom out. I just want you to see the 3 questions that we did from this one. Right here, notice in this one, they said that their mean score, again, average. So again, bar X.
Right.
Don't
Right, yeah.
sample mean, notice again, bar X. Well, look why this one tricky. Notice that in the first question right here, the average daily cost, average bar X. Well, look how part A tricky now. Part A now have nothing to do with no bar. So part A is what?
Standard
Part A is just
deviation.
regular normal distribution.
Distribution. Oh,
Yeah, so part A is just regular. So that's another keyword you have to look out for. Part A is just a regular normal distribution. So that's how they like to mix them. So now we can just say the probability X is what they want?
less than 850.
The less than 850. So standardize it for me.
Probability that X is less than 850 minus 900 divided by 25.
25. This now have nothing. Remember, we're using X. This now have nothing to do with the sample size. Only bar X have to deal with sample size. This one have nothing to do with sample size.
Divided by 110.
Divided by the square root of 110.
Okay. Yeah.
Remember that when they give you variance, this is variance. So to find the standard deviation, remember it's the square root of the variance.
Right.
Yeah, so that's a square root 110. So now we can work that out. 850 minus 900 is negative 50. The square root of 110 is 10.2. All right, that's too much work for me to do mentally. I'll wait on you.
Hold on. The square root of 110?
Yeah.
10.4.
10.4. Yeah. 10.48. Yeah. All right, so negative 50 over 10.48.
Negative 4.77.
Negative 4.77. Very good. So now your table won't have 4.77, but my table has it. So I don't know why they're putting these on the problem set and they know that it only go up to 3 point something. So now in this case, it works out to be 1 minus the probability Z is less than 4.77. And 4.77 is 1. Believe it or not, this is 1. So this is now 1 minus 1, which is 0.
0.
In other words, they're telling us that there's no chance that a resident consume less than 850 kilowatt hours. But I'm very happy they said this because I don't consume that amount of light. I'm very happy they said residential utility customer. So they're trying to nice it up to not say it's a very wealthy person. So them graft on their light bill. So they use a lot of power. But That's fine. Maybe it's a large family. We don't know. We can't assume. 900.
They have AC and all of those things.
Yeah,
and
maybe it's an
driver.
extended family. Let's not assume. But it says a resident, but we don't know what if that resident lives with a large mass. So let's not assume. All right, part B now. Part B. Hold on to part B.
Probability that X
Bar X now. Once it's a sample average, bar X.
bar X um, is less than 850 kilowatt hours.
840, yeah.
840 kilowatt hours.
So now we need to work this out. So standardize it. So Z is less than
840 minus 110
minus 110
square.
minus 110. It's always minus the mean, always minus the mean.
Oh yeah, minus 900
100 over
110, the square root of 25.
so the square root of 110 over 25.
Okay.
All right, good. So now we just need to work that out, which I doubt that will ever happen. 840 minus 900.
It's in the what it is. 840 minus 900. On the bottom. Square root 110 over 25 income. Negative 143.01. That's what you got?
Negative 143.
Yeah.
All right, when I put it in my calculator, I get negative 28. So 840 over 840 minus 900, that's negative 60 over the square root of 110 over 25.
Put it in again, minus 900. Put on the bottom, fraction sign 110. In the square root sign 110 over 25.
You got it now?
Now same thing I get in.
All right, how did you put the square root right there? So press fraction first, 840 minus 900, go down, press square root first, then fraction button.
Oh, I put the fraction button first.
Oh yeah, square root first, then fraction
840
button.
minus 900 square root and the fraction button 110 over 25. 28.63.
Very good, negative 28.63. In other words, that's 1 minus the probability Z is less than 28.63. So it's 1 minus 1, which is 0. Because really and truly, we already knew that it would be 0. Because once 850, if nothing was 850, then nothing worse than I reach 840.
Yep.
Yeah, so we already knew before we did the question that this should have been 0. So I don't know why they put these two back to back on the paper, knowing that once the first one was 0, The next one was, that's poor practice. That's poor setting up of questions for practice. You want to have more disparity. Disparity in the sense that you want to do a different variation of the questions.
Questions,
So
yeah.
you want, when you get the test, you cover all the different styles of question, but they're not doing that. They're giving you the same style of question back to back.
Well, maybe they don't know how to do
No,
it.
they do know, they do know. Because on the test, you'll find that they give you it in different styles now that you wouldn't have been accustomed to. So why not just mix it up in the problem set like where you mix it up on a test? Same thing. Just mix it up. All right. So now, the next thing we need to look at now is proportions. All right. The next thing we need to talk about is proportions. All right. Now, proportions is really in set 10 with hypothesis testing, but I like to do proportions with sampling distribution. Why? Because it makes hypothesis testing way easier. So we'll only look at one proportion question now, because proportions is in problem set 10.
Okay.
I like to just do it with I like to do it with sampling distribution because it's still a sampling distribution question. So what is proportion? The word proportion, as it means, is ratio. Part of a whole, proportion. Right? Call it that? That's
Yeah,
a proportion.
right.
Part of a whole. So since proportion is part of a whole, what we're saying is that the average proportion for any variable, when we're using the central limit theory, we say P hat now. P for proportion. So P hat gonna follow a normal distribution with, remember it's a mean, but with mean now, proportions mean with probabilities. So it's going to be P, the probability of success, comma, the variance for proportion is found by P times Q divided by N. You might see people put hat above it to show that it's the probability of it we're talking about. So it's P hat Q hat over N. That gives you the variance of the proportion.
Okay.
So remember, proportion is just probability. So probably we're looking at a case where, let's say, Charmaine is going to send Anne to observe the salary of 200 finance persons in St. Anne. And then you're going to observe 400 persons in Kingston. And maybe from your observation, you found that 80 out of the 200 obtain a salary above 175,000 per month. I'm just saying that. So now, with that, you'd say, oh, so out of my sample size, 80 out of the 200 get that. So then that would be a P, a probability of the success. Your P is 80 over 200. You'd simplify that to get, in this case, I think that looks like 0.4. So that would give you a P. Once you get your P, you know your Q is 0.6.
Right.
Yeah. So that's all is proportions. Instead of dealing now instead of dealing with it in the regular form now, it's just in proportion form now.
Okay.
All right? So that's all. It's literally the same thing, but now just with proportions. This is where now we need to talk about the continuity correction. As we're moving from discrete to continuous, we're going to use a continuity correction of plus or minus a half 1 over 2n, 0.5. This is where we're going to use the continuity correction. All right?
Okay.
Don't worry about that for now. So let's look at this example right here. It says, in a survey, 500 mothers and fathers We're asked about the importance of sports for boys and girls. Of the parents interviewed, 60% agreed that genders are equal and should have equal opportunity to participate in sports. Describe the sampling distribution P hat of the parents who agree that the genders are equal and should have equal opportunities. All they ask you is to write down the sample proportion. Sample proportion, remember the sample proportion P hat follows a normal distribution with the proportion success P, comma, PQ over N.
Right.
But P in this case is 0.6, 60%.
Right.
So in that case, we can tell them the sample proportion follows normal distribution, 0.6, comma. Now we just need to work out Q. Q would be what?
0.4.
Good, divided by 500. So 0.6 times 0.4 over 500. Work that out for me. Or you can even leave it as it is like that.
0.6.
How much you got?
0.4, hold on, divided by 500 equal. Oh, God. Um, 4.8 times 10 to the negative 4.
Good. 4.8 times 10 to the negative 4. And that's our variance now. And that's it.
That's it.
Yeah, they just wanted you to describe the sampling distribution. This would be the sampling distribution. They didn't ask us to do any calculation.
Okay.
Yeah, keyword describe. All right. Now here's a question that involves some calculations. As I said, we're not going to do any question with sampling distribution. I just want you to make note of the formula because we're going to come back to it. We'll look at hypothesis testing next week, okay?
Okay.
So that's the only reason why we're looking at it. Hypothesis testing, we're going to talk about one-tail and two-tail tests. I'll just show you right here next week. We're going to look a lot at it when you look at questions like these now. If a machine is 5% defective, blah, 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 test at 1% significant level, whether or not the machine needs to be realigned, write down the null and alternate hypothesis. This is hypothesis testing. So you notice it's heavily done in chapter 10, but as I said, I like to look at it with sampling distribution because we actually use a sampling distribution technique because they have to give you N. You get what I'm saying? So that's why I like it right there. But to each his own, they'll put it at different places based on when they do it. But I like everything to have a, you know, I don't like when it's fluid. It's fluent. I like when it's fluent. Cool?
Okay.
All right, can you give me a second?
Sure.
All right, sorry about that. All right.
Okay.
All right, let's go. So this one here, it says, it found out that 2% of trees in a plantation have a certain disease. 2% of trees in a certain plantation have a certain disease. Cool?
Yeah, man.
But what they're telling us is the proportion is 0.02. Cool?
Right.
So then Q is going to be what?
0.08.
98.
98, right. And 98, right.
Then they tell us a random sample of 300 were examined. So N equal 300. Then it says, find the probability that the proportion of the diseased tree in the sample is less than 1%. In other words, they're asking us, look at what they're asking us. Before we look at what they're asking us, let's write down the distribution. So P hat follows a normal distribution P 0.02, comma, it's then remember P times Q over N. So you work out P times Q over N. So 0.02 times 0.98 over 3 bills.
300, right. Negative 3.2 to the negative 3.
How much you got? Well, you got negative. We can't multiply positive numbers and get negative.
Hold on. I did a subtract. 0.02 times 0.98 divided by 300. 6.5.
Good. 6.53
3
times 10 to the negative 5, right?
times 10 to the negative 5.
Yep.
Where I get that from? Oh, yes.
Yeah, it's there. It has to be there.
Yeah.
So that is now your sample proportion variance. So now we can go ahead and work out what they ask us. They say find the probability that the proportion of the disease tree in the sample is less than 1%. So we need to find the probability. So the probability, the proportion is less than 1%. 1% is 0.01, right?
Right.
Now, I know this looks weird for many persons. Many persons probably say P in bracket P. Yes, this P represents proportion. In the same way how we standardize X, we can standardize P by changing it to Z. So this becomes Z is less than, your P is still a X, so it is now 0.01 minus your mean, 0.02, divided by the square root of your variance. Square root of your variance here. So literally it's the same thing, it's just that because we're seeing some new variables, P hat. So now we work that out. 0.01 minus 0.02 divided by the square root of 6.53 times 10 to the minus 5.
You get a negative figure?
Negative, how much you get?
1.287.
Negative 1.28.
7
Negative
times 10 to the
1.
negative 3.
Wait, this is what I have when I put in the calculator.
I get 10 points. Oh, hold on. All right, so is 0.01 minus 0.02. Square root first.
Square root.
and 6.53 times 10. Where's the empty box? Minus.
You got it now?
I got an error.
Did you put, when you say raised to, how did you put in this minus for?
I put the empty,
You
the
put
empty
the-
box.
Very good. X to the box, yeah.
0.1 minus 0.02 square root 6.53 times 10 minus. Why I have two empty boxes though?
Why have two empty box?
All right, after you put 6.5, you have, after you put 6.53 times 10, what you put next?
Times 10, then you put the, all right, let me just retype to say type along with me, the 0.01 minus 0.02. Then you put square root next.
Hold on, 0.01 minus 0.02 square root
Then you put the 6.53.
6.53.
Then put it times 10.
Yeah.
And you press this X box.
Which X box? Oh, put the X box, right?
Yeah. Minus 5. That's it. Then press equal.
X box minus 5. Oh. Okay.
Now we get our smooth answer. So Z is less than negative 1.2, negative 1.2 what?
37.
37. No, 37 is not helpful to us. So we're going to write negative 1.24. Remember that our table only gives us 2 decimal places for X and Z.
Okay.
Right? Yeah, or table only gives us 2 decimal places. So now, hey, let me see something. I was just looking at the normal table that they sent, because it still puzzles me why you've never heard your lecturer use the word phi. It just really annoys me that you never hear phi.
If I use no 5.
Yeah, that's crazy. And phi is the definition of normal distribution. So that's really, it's perturbing for me because this is the area I really want to specialize in. So it's perturbing to know she don't use the correct terminology. All right, so let's go now.
Ask other students if they never hear 5.
Repeat.
I said ask the other persons that you tutored.
Okay, yeah, I will ask. I will definitely ask. Because that's really perturbing for me. But let's go. So now once we get to this stage, it's just 1 minus the probability Z is less than 1.24. They will look in our normal table. What's that for Z less than 1.24?
1.24. 0.8925. 1.24.
Yes, you're correct. 0.8925. So that's it. So 1 minus 0.8925. And that works out to be, what's that?
0.10.
0.10 what? 75?
75, right.
Very good. That's your answer. Right? Nice. Okay, answer. Very good. And you know what's funny? If you Google any normal distribution table, you see the phi. If you Google any normal distribution table, you'll see the phi.
Even when they're doing the problem sets,
Yeah, they don't use it.
I know you should say nothing but 5. I usually say plus 0.5.
Yeah, understand. Yeah, I know how she do it now. She just ignore the 5. So what she literally do is tell you the SWOT. She tell you the formulas to SWOT for each, for when it's less than, greater than,
Right.
less than, negative. So you don't understand the definition of where it comes from. She just tell you to SWOT these and use it. I don't like when you SWOT it and use it, because if the question twists, then you don't know how to apply it. So I don't like that way, but so the normal distribution table PDF. Just Googling it to show you the 5 in an actual table, apart from the ones that they upload. So I'm going to the one from Google here. It's loading. So this is one right here. So do you see this in from Google?
I'm seeing it. Yeah.
Notice the key thing, it says what? 5.
5 of Z.
Yeah, for negative values Z, we use phi of negative Z is 1 minus phi of Z. I can't believe she don't teach you the definition. That's the definition of normal distribution. You can't just learn the SWOT formula. Come on, man. And I realized that also for here, I noticed that as I was about to show you how you get the formulas for each, I noticed that you don't need the formula. She give you the SWOT method again. These are the numbers that you must know for the inference for mean. So I'm not going to teach you to just look at these numbers. I'm going to show you the formula that we're going to always use, which is the definition of inference for mean. I don't like to just go by swatting some numbers and plugging in. Because if the question is structured in a different way, we can't apply it. So I don't like this here that she used. So we're not using this. Or let me say we're using it, but we're not using it directly. So that's what we're going on to know. So now we're looking at inference for mean, also known as confidence interval. So you know our style already. Before we get into confidence interval, we like to talk about why we do what we do. So this is really estimation. So look at this now. Whenever we were talking about binomial distribution, there were 2 key things we focused on, N and P.
Right.
We need to focus on N being the number of observations, P being the probability of success.
Right.
If it's normal distribution, you focus on mean and your variance.
Mm-hmm.
In general, what we're saying is when you're doing distributions, you always have to have your parameters. All right. And if you're using a sample, you have to have your statistics, right?
Right.
So now we're saying let theta be any of these population parameters. We don't know. Now, sometimes, right? Sometimes you may not know your true actual parameter values. You may not necessarily know them. But what you do know is what we call an estimate of those values. What you do know sometimes is the estimate of those values. So what we're saying now, Charmaine, is that if you know an estimate of, let's say, for example, in your Econ 1005, let's say you don't know all the grades of all the students, but you know that from the 2 mid-semesters, you can gather that maybe the average grade for Econ 1005 is 15 out of 30 on the paper 1. Let's just say that, safe to say, that's the average grade, 15 out of 30. Now, notice that you didn't go add up everybody's grade and find out if it's actually 15 out of 30. That's just an estimation, right?
Right.
But there must be some sort of level of accuracy of your estimation. So this is where we talk about confidence interval. So if you're 80% or 90% confident in that estimation, then you can find the true range where all the values would actually lie. So like how I just stated that maybe the average grade is 15 out of 30, then maybe the truth of the matter is that everybody grade might be between 12 to 18 out of 30. Or maybe I can say 95% of students get between 12 to 18 out of 30. That might be true. How
Yep.
did we get all of that? It comes from a topic known as confidence interval. So all of this bag of chatting right here, telling you about margin of error, telling you about left margin, right margin of error, error of estimation, unbiased estimator of P, unbiased estimator of the variance is standard is the standard deviation square. All of that bag of chatting right there, we just summarize it. So skip out all of them bag of chatting there. All right? Holy for chatting. This is where the real things start now. So as we're saying now, if we want to know, for example, the proportion of a population, we can find an estimate of the sample, and the sample is good enough to represent the population. So an unbiased estimator for P is P hat, which is found by X over N. An unbiased estimator of your mean for your population, remember parameters are for population. So an unbiased estimator for the population is your bar X, and bar X is the sum of X over N. Meaning you can find the average of a sample, and your sample can be representative of the entire population.
Okay.
And finally, an unbiased estimator for sigma square, which is your variance, is found by the variance formula, the same one. But only time we have enough frequency in it, but same formula. 1 over n minus 1 times the sum of x squared minus the sum of x all squared over n. Use this formula so much that we're supposed to sleep on it just in our mind.
Mm-hmm.
All right? So yeah. So now let's look at a question here where we're going to use all of that together. So here's a question that's, the heights for students in a class are as follows. Now these are all made up. So don't think that students in a class follow these numbers, because this is a height in centimeter, 188. This is 6 feet 3 inches. This is 6 feet 5 inches. Like, what kind of students them here?
Giant.
Yeah, so these are just some made up numbers. It's not necessarily true. So let's not even get into the logistics of the numbers. But it says, find the following, an unbiased estimator of the mean. Now, an unbiased estimator of the mean is just bar X. All right? So bar X would just be, it's just finding the mean. Add up all of them and divide by how many students. So that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 divided by 10. We add all of them up. 156 plus 160 plus 164 plus 168 plus 172 plus all the way up to 192. Whew, add them for me.
156 plus 160 plus 164 plus 168 plus 172 plus 176 plus 180 plus 184 plus 188 plus 192 divided by 10. 174.
174, very good. So that's an unbiased estimator of our mean. Now, an unbiased estimate of our variance now, what's the unbiased estimator meaning? This is just a sample of the students from the class. Now, we're saying that the average height of students in the class is this. Now, that's not necessarily true. How can we just select 10 students and then give the average of the class, but it is representative of the class, so that's why we call it an unbiased estimate, because we actually use numbers and work it out. We actually use a sample, so it's unbiased. Now, an unbiased estimate of the variance, remember, variance S squared is 1 over n minus 1, so 10 minus 1 times the sum of x squared minus the sum of x all square over n. N is 10. We already know the sum of x squared. The sum of x squared is 1,740.
Right.
Just need the sum of x squared now. So the sum of x squared, remember, you add up each of them squares. So 156 squared plus 160 squared plus 164 squared. You continue square all of them. Let me help you all. Let's bring out the calculator as well. Is the height increasing by 4? That is so stupid.
156. Yes, it is.
Yeah, I just noticed that everybody height increasing by 2 inches or 4 centimeters. That's stupid.
Plus 160 square plus 164 square plus 168 square plus 172. This is from the packet?
No, no, no. This is from the notes that I'm going to send.
Plus
We're going to get to
178
the packet after this.
plus 180 square plus 184 square plus 188 square plus 192 square equal.
You got that?
Yeah,
Good. 304,080
and 80.
minus now the 1,740 squared over 10. We can put all of this in the calculator one time because our calculator is smart. 1 over 9, open bracket, 304080 minus fraction button in bracket 1740 close bracket square over 10 close the bracket. Put all of it in our calculator one time and we get, that's our variance. Our variance is 146.7. That's our variance. Which makes sense because then the standard deviation is roughly 12. That's about true.
Yeah.
All right, now this one right here, part C, says we want an unbiased estimate of those titles greater than 180. So remember, proportion is just going to be X. X in this case is how much people height greater than 180. 1, 2, but it's actually just 3. Greater than 180 is just 3. 3 out of 10. So these are the 3 persons that are basically 6 feet and above. 3 out of 10.
10, right.
All right. That's that. Now, why did we do that? We did all of that to get to confidence interval now. Confidence interval, not going to get into the nitty-gritty of it. I just want you to know the formula. This is the formula that you're going to need to remember. It all is going to be summarized by one formula. I'm skipping out all of that is the proof of the formula. Everything here is the proof. You don't need to know the proof. You're not going to get a proof question ever. All right, unless you go on to do sampling methods next year, but apart from that, you won't need to know the proofs. So this is the formula that you're going to need to remember now. It's summarized. Here it is.
Bar X.
Bar X, a confidence interval for a
Plus or
mean
minus.
is this. So this is your confidence interval now. So the confidence interval for any mean or for any average is bar X plus or minus Z alpha over 2 in brackets sigma over the square root of n. Now remember, I was giving you a question and I said, remember when the probability is 0.1 is 0.95, and I said you should automatically know that it was 1.96 and negative 1.96.
Right.
Now we're gonna see why it was important that we knew that. So even though they didn't tell exactly confidence interval yet, we were to use principles of confidence interval to do some of the earlier questions in the packet. So I remember we were looking at it explicitly. Oh, now we're finally there, right?
Yeah.
So now this is a formula you need to remember. That's it. Literally, that's it. Literally, one formula. So Charmaine, I want you to write it so much time till you can't forget it. Bar X plus or minus Z alpha over 2 in brackets sigma over root n. Write it again as a wake up. Bar X plus or minus Z alpha over 2 in brackets sigma over root n. Before you go sleep, write it. Bar X plus or minus Z alpha over 2 in brackets sigma over root n. The more you write it, the more you remember it.
Okay.
All right? That's all I'm saying. Once you keep writing it over and over and over, then you just can't forget it. Like, how can you forget what you write 50 million times?
Okay.
Yeah. So now we're going to look at how we're going to use it in a question here. So a question might come like this now and say, the reading age of children about to start secondary school is a measure of how good they're at reading and understanding printed text. All right, so they're giving us a BA chatting. No one read none of them stuff there. So part 1, calculate an unbiased estimate of mu and sigma square. So unbiased estimator of mu, always remember unbiased estimator of mu is bar X. Bar X, you know, is the sum of X over n, don't?
Yeah.
In that case, it's going to be the sum of X they give us is 232.6 over n. Let's say n is 20. So put that in a calculator for me.
2.3.6 divided by 20. 11.63.
11.63. Good. Now we need to work out now sigma square. Now remember, sigma square is going to be equal to sigma square. The unbiased estimator is S squared, and S squared is equal to 1 over n minus 1, so 20 minus 1, which is 19, in bracket the sum of x squared, which they give us, minus the sum of x all square, so 232.6 all square, divided by n, and in this case is 20.
Last right there, so.
Repeat?
Last at sigma square.
All right, no problem. So we just did it a while ago, right? This formula is what we're using. An unbiased estimator for sigma square is standard deviation square. And the standard deviation formula is 1 over n minus 1 times the sum of x squared minus the sum of x all square over n. Just go back to long time standard.
Is that the variance square?
Yeah, this is standard deviation square, which give us variance.
Oh, standard deviation. Okay.
And in this question, n was 20. So the 20 minus 1 is, oh, get 1 over 90. In bracket, the sum of x squared, they give us the sum of x squared. So the sum of x squared here. That's how we put that there.
Okay, right.
So all we're doing is plugging into the formula.
Okay.
So now we just take out our calculator. Take out our calculator, put all of that in it one time. 19 in bracket 2756.22 minus fraction open bracket 23.26 raised to the second power over 20. Put all of that in the calculator one time, and we'll get with 2.69. $2.69, yes. Now, the next part is where we really need to focus on. When they're gonna ask you this now, they say find a 90% confidence interval for mu, given that sigma square is 5. So they're telling you now, given that sigma square is 5, you're gonna have to remember that the confidence interval is bar x plus or minus alpha over 2 in bracket sigma over root n, right?
Right.
In this case, we already work out our bar x, which was 11.63 plus or minus. Now, I was thinking about teaching you with my table, but I don't want you to use my table when that's not how they're going to do it. So I want you to look on this. Here it is. Here it is now. So the normal table that they give, not the normal table, where am I looking for it? They give you a table that they want you to know. So I want you to stick with their method here. This is the table that they want you to know. When it's 10% confidence interval, this is your Z alpha over 2 that you use it.
Okay. Oh, this is a problem set 9.
Yeah. So this is the value we're going to use, 1.645, all right? Once it's a 90% confidence interval, we use 1.645, cool?
Okay.
So now we're going to just use our 1.645. Oh, let me close sampling distribution, we'll finish that. 1.645. So right here it is 1.645 in brackets. Sigma, now they tell us sigma square is 5. So if they tell us sigma square equal 5, what is sigma, Charmaine? If I told you that x square equal 9, what is x?
3.
3. So if sigma square is 5, what is sigma?
25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25. 25
How much?
25
No, so sigma would be the square root of 5.
square root of 5.
You have to square root it, yeah. So in that case now, sigma is the square root of 5 over the square root of n. But n is what? N is 20. It's over the square root of 20. So now we need to work out this side, Charmaine. Look how it's gonna get very easy now. Literally, this is all there. All you need to know is just one formula and you're happy for life. You're happy. So now we just need to work that out. So we're gonna get 11.63 plus or minus. Now let's work out this part now. So let's bring up our calculator. You're gonna work out this part of it now, Charmaine. So what you're gonna do is put 1.64, open bracket, fraction button, square root 5 over square root 20, close it. And you get 41 over 50, which is 0.82. Now, when you get that, Charmaine, what you're going to do is put like an open bracket and a closed bracket and a comma in the middle. Now, the first value you're going to work out is 11.63 minus 0.82. So 11.63 minus the 0.82. What we end up get is 10.81. Then you're going to work out now with the plus button. So now you're going to change the minus to a plus. You're going to end up get 12.45. So what we're saying then, Charmaine, is that's part 2. That's our confidence interval. Now, I love when questions ask stuff like this now. Interpret the interval. What the interval is telling us then, Charmaine, this part is even more important. 90% confidence interval mean we have 90% certainty. So we are, this is part 3, we are 90% certain that the mean lies between 10.81 and 12.45. All right, and that's the age at which students, this is the mean for the age at which students learn to fully read properly, between 10.81 to 12.45 years old. We're 90% confident that's when they master reading. I agree with this number. This is when we're at our best in terms of reading and writing. Well, not writing skills, in terms of reading ability, 10 to 12. Do you agree with those numbers? I'm not hearing you anymore, Charmaine.
What
Can
you
you hear me?
said? What you said?
Oh, I'm saying that, do you agree that these are the numbers where our reading ability is at its best? Reading, not writing, reading ability.
What age group?
The age is from 10.81 to 12.45. So almost 11 years old to about 13 years old.
90%?
Yeah, we're 90% confident that that's when students fully master reading printed text and stuff like that. I believe it.
Okay.
I think this
Yes,
is true
yes.
because at that age would have been doing, would have finished
Primary level.
primary level, where you know they test us a lot on communication studies and
Right.
all that stuff. So I believe that our reading was at its best that time, and then from there it dissipated little by little by little. Yeah. But that's that. That's how the confidence interval. So literally you just need to remember one formula. So let's look at the problem set and you realize how easy this topic is. This is the easiest topic in everything. Let's look at this one right here. So I highlight it. Now I'm gonna copy it and go to the blank document. No man, it's weird. Why they always use one topic over and over, man? They gone back for the electrician again, you know. We just do an electric company and light bill. No, they use electric. They can't mix it up, man. Variation make it nice. No variation. All right, let's go. So this question here, it says, an electric company wants to estimate the average number of hours that a light bulb made by a company will last. A random sample of 40 light bulbs was selected, and the average burning time was 1416 hours. 1,416 hours. I want that light bulb. Let me see. I'm just doing the math right here. 1,416 divided by 24. There's 24 hours in a day. Oh no, I don't want that light bulb. That light bulb only lasts 2 months. I don't want that light bulb. No, 59 days. That's
Won't even reach 2 months.
Yeah, it don't even reach 2 months. I don't want that light bulb. It's so they make it sound sweet. This is how they're gonna do it in when you're trying to sell stuff. This is how you want to phrase it. People go in the store and say, yo, this light bulb would last you 1,400 hours. I know people gonna say, what?
Yeah, so you have to do the calculation to know so it doesn't
Yeah.
make sense.
And if you don't do the calculation, I guarantee you're gonna buy it. Then 2 months later, you go down there, go cost the people, and the people might say, I did not lie to you.
This is true.
They just use Sykes. Why are they using so much Sykes? Why they can't honest and put what people want to say? 59 days, oh, me now buy it.
But they're not dishonest, they told you.
Yeah, they tell us, but they're not being
told.
very direct. They're not being direct. People want direct honesty. Be direct. Come on, man. Nobody wants to say hours and these big numbers. Big numbers flawed or
because I know that's
flawed us being the correct thing. So let's go now. It says a random sample of 40 light bulbs. So they're giving us n equal 40. Now they said the average burning time found. Average is what? Bar X, don't?
Yeah.
So they give us bar X is 1416. Then they said the standard deviation is what? 30. So they're giving us the standard deviation. You couldn't ask for an easier question than this, because now you just use the formula, construct a confidence interval. So the 90% confidence interval, 90% CI, it's given by bar X plus or minus Z alpha over 2. But then you know that you just go to this right here for 90% confidence interval, 1.645. So you put that right there. 1.645 in bracket, sigma, your standard deviation divided by the square root of n. They already give you bar X, 1416, plus or minus 1.645 in bracket. The standard deviation is 30, divided by the square root of 40. Okay. Tell me if this topic don't really easy. You're just plugging in numbers.
Once you can identify the different parts.
Once you identify, it's very easy. So now let's work out what this part is. The 1.645 in bracket 30 over the square root of 40. 7.80.
1.645, go again.
1.645 times 30 over square root 40.
Oh, times. Okay, 1. 1.645 open bracket square root 30 30. We get 7.80.
Yes, 7.80. So now, remember the first value is when you subtract the 7.80 from 141.
Yeah.
When you subtract it, what you get?
1416 plus or minus 7.80. 1416 minus 7.80. 1408 for the minus one.
Point
2.
0.22. When you add 7.8 now, it is 1423.88, right?
1408.2 plus 1416 plus 7.80 equal 1423.80. Yeah.
So good. So in that case, we're saying we're 90% confident the light bulb average life is from 1.08.2 to 1423.8. We're 90% confident this is where the average will be between these numbers. True mean, the true population mean.
Yep.
All right, so you're gonna walk me through the next one. So notice how that question was easy. Just give me a plug it here. My gosh, couldn't have been any easier. All right, so you're gonna do these two, and then we'll look at one of the questions from the packet. And then we're good. So let's look at this one here, number 2. You're gonna walk me through number 2.
So number 2, so the lecture index for statistics explained that in this class we have a mean of 55%. 55% and a random sample of 100 students is taken and the mean is found to be 69%. From previous years, it is known that standard deviation is 4.4. Test at 1% level of significance that the lecturer has understated the true mean of grade of the student. So, what is
So tell me what they give you. What does this 55 signify? Write down what they give you. What does a 55 signify?
the 55 is N.
Is N?
Yeah.
Percent?
Hold on.
Percent can't be N.
Oh, N is 100.
N is 100.
Right. So N is 100. And bar, the mean grade is 55%.
Very good. Bar X is 0.55. Good.
Yeah, 0.55. That is bar X.
No,
And
this is the claimed bar X. Remember, that is the claimed bar X.
the claim bar X, right?
Yeah, this is what she claimed.
And then the
standard sample now
is 4.4.
Repeat.
The standard deviation is 4.4.
Standard deviation is 4.4. Good.
Right. And it says
What
one.
about the 69%? What is this 69%?
Is that the CI?
This is now our sample mean.
Sample mean. Oh,
And that's the one we always work with, the sample mean. Sample mean, sample. It says, and is taken and the mean is found to be, that's the sample mean. Cool?
okay.
Good.
So that is 0.6669.
9, good.
Okay.
Then it says test at 1% level of significance. When they say 1% level of significance, in other words, test at a 95%.
9%. 99.
Confidence interval.
Oh, okay. Okay.
If they say test at 5% significance level, it will be how much confidence interval?
50.
If it's a 5% significance level.
That would be like 95.
95. If it's a 10% significance level.
90.
Very good. You catch the drift now. Good. Tell me what's the formula again.
So the formula is 99%.
So what's the formula for 99% confidence interval?
It is 2.576.
Before we reach the Z value, formula.
What is some name again? This will tell you. Bar X plus
Bar
or
X
minus, right?
Plus or minus.
Z is 2. Open bracket, sigma over square root of n.
Very good. Which one you gonna use for bar X? Because you told me 2 bar, you told me the claim bar, you told me the sample bar. Which one you gonna use?
The sample bar.
Very good, the sample bar. The 0.69 plus or minus 99%. What's the Z value? Let me go look at it.
Hold on, let me see now. $99%, 1.960.
No, you told me the correct one first. 2.576.
Oh, yes.
That's 99.
99%, right.
So now it is 2.576.
0.69 plus or minus 2.576 open bracket.
Sigma, the standard deviation is 4.4.
Yes.
Over the square root of 100 because n was 100. So now we just need to work that out. We need to work out this part first.
Yeah, I know.
Yeah.
2.576 bracket square root of 4.4. One point 1.13.
Good. 1.1. Now, usually we don't need to go so much. Just go 2 or 3 decimal place. So 1.13 what?
3.
3. So in that case now, we can 1.13.
1.1.
Yeah, you're correct. You're correct. Yeah. So in that case now,
0.69.
work it out now. 0.69 minus 1.13.
0.443.
How much you get?
0.433.
No, 0.69 minus this.
Yeah. 1.1. 0.443. And let again.
0.69 minus 1.133, negative 0.443, but because we ignore the negative, yeah, 0.443. You're correct.
Laptop dying. Hold on, laptop dying.
All right.
Okay. So the other one is 1.823.
Good, but when you get 1.823, right?
Yeah.
We're just going to put 1. Why do we stop at 1?
Because it's supposed to add up to 1. It can't be more than 1.
Yes, because we're talking about what? We're talking about students' grades. So we're saying
Right.
that we are 99% confident that the PPLM grade gonna average from 44.3% to 100%. So 99% confident the class average is between 44 to 100. We're almost certain say that's the range where it lies. Cool?
Yeah.
All right. So let's look at one from now. The problem set. I did underline them, the one we're gonna do. Here's the first one where it started. It says random samples of size n were selected from a population known with a standard deviation. How is the standard deviation of the sampling distribution of the sample mean affected if the sample size is increased from 50 to 200? How does that affect the standard deviation? So you see how the word up now, the formula what we need to know, right?
Oh.
So now this is where, don't worry, don't get frightened. We need to just
Divided
remember the
by-
formula.
It is divided by 2.
So let's look at it. Remember, this is a formula for the standard deviation of the sampling distribution. Sigma x is just the standard deviation divided by the square root of n. Isn't that so?
Yeah.
So let's observe with some random numbers. You can use a random number, you know. Let's say sigma was 20. Let's see what's gonna happen now. So if sigma was 20 over the square root of 50. What is that? $20 over square root 50.
2.8.
2.8?
2.82.
2.82. Very good. 2.82. 2.83. Or some might say 2 square root 2. Doesn't matter.
Yeah.
Now look at this now. Now we need to see what happened when n is 200. So we're using the same sigma value 20, but see what happened. Sigma bar x is now 20 over square root 200. So work out that now, 20 over square root 200.
2.
We get
Two.
square root 2, square
Two,
root 2. We get square root 2. So notice that it go from 2.82 or 2.83 to 1.41.
4.
What happened there? When we increase it,
You get a lesser value.
to 200, the standard deviation decreased
Right.
by half. In other words, it is divided by 2.
2.
Right? That's option D. See there? 2.82 divided by 2, it was 1.41. So that's how you check out that. And all you had to do is just remember this formula. See, so they can word it up and then check if you understand the formula. That's all they're going to do. They're just going to word it up. They can't do anything else. Let's look at the next one here, because 15 is also sampling distribution. It says, let X be a random variable that is bimodal distribution with mean 12 and standard deviation 1.5. Based on the random samples of 400, the sampling distribution of mean is. So first thing is, they're asking us to check out this formula again. Remember, the mean don't change. So in this case, the sampling distribution of the mean bar X will follow. It'll have the same mean of 12, but they'll just need to work out the standard deviation over here. So, but the standard deviation of the sample distribution is the same formula. Is the standard deviation of the normal distribution given divided by the square root of the sample size, the square root of 400. So just pop out our calculator, put in 1.5, divide by the square root of 400. That will be our standard deviation.
That is 0.075.
Very good. So it will be approximately normally distributed with mean 12 and a standard deviation of 0.075. You see, all they're doing is checking if we know them formula there. Easy, don't? Nice. All right, that's not that yet. Notice they're talking about right here, standard error, margin of error. Remember standard error, remember I told you the first thing at the start was to write down that sigma over square root n. We call that what? Standard error.
Standard error, yeah.
I want you to look out for that. But the only reason I'm skipping that question is because we need to do the next one before, the next topic before we can look at it. The very first thing is, we called it the standard error. See it here, right here, standard error on bar.
Same thing as distribution mean.
Yes. So just to remember it, yeah, but we're not going to do this one because we don't look at margin of error yet. We need to look at confidence, not confidence interval, hypotheses. Then we'll do that one. Another hypothesis. We do that's next week, hypotheses. All right, this is still hypotheses, but we can do it. It says you test a claim more than 10% of the adults have tattoo. Your statistic turns out to be Z equal 2.31. What is the p-value? So the only reason I look at this was this is 90% confidence interval. Once you see 10%, it says you claim that more than 10%. So it's 90. All right, no, we look at it when we look at hypothesis testing, because we're gonna have to get into something that don't want to get into in that I have to elaborate on. So take off that. This now, 21 is confidence interval. So we looked at two questions, that is sampling distribution. No, it's confidence interval time. We'll just do this confidence interval one, we good. So they say a random sample of 450 vacationers. So N is what?
450.
Always write down as they go along. Showed that 150 were business executive. We want to create a 90. So they tell us that bar X is how much?
150.
150. So bar X is 150. Then they say we want to create a 95% confidence interval for the proportions of vacationers who are business executive. So now, all you need to write, it says, what is the value at the center of the 95% confidence interval? All right, so write the symbol and the value. So all you're asking you is to look in the table and tell them what is that. So Z
Always 1.960.
very good. The 1.96, right?
Right.
Now, what is the critical value for this confidence interval? All right, so we just wrote it down. The value of the center is the same as the critical value.
It's a write both the letter and value corresponding to the interval. So you're going to write it again?
All right, no, I think this is where they're asking us
But
to
to
write
write the
down bar
symbol
X.
of
Right, bar X. Write down the confidence interval now. Critical value, I guess this is what they mean now. Bar X plus or minus 1.96 in bracket sigma over the square root of n. And you'd substitute, but this question didn't give us sigma. So that's the issue. This question didn't give us the standard deviation. They didn't. Maybe they did. Let's see, let's see.
Look at the question again.
Yes, they did. My apologies. You don't see what they said
The
right
proportion.
here. Proportion. So I am totally sorry there. I am misconstrued. So that's why we have to read it properly. So now we know this is a proportion question. Now you see why I like to teach the two topics in one? Because look how they might teach proportions after confidence interval, but give a proportion confidence interval. Do you get what I'm saying?
Mm-hmm.
No, just look at it, look at it.
Yep.
Plausible.
All the time they do it.
They are going to teach confidence interval without proportion. Then they're going to put proportion in the question, assuming that students are going to be able to transition the knowledge. And I'm saying that is BS, that is stupid. You cannot do that. You cannot do that. But that's what they do. So see it there? That's why I'm glad that we do proportion, so we are fine. So we know proportion now.
P
we can work out P hat. We know it's X over
normal
N.
distribution.
Yes, so very good. So write down our P hat follows a normal distribution with P, the success, but let's work out the success up top here. It's X 150 over 450, which is 1 over 3, right? Convert to put 0.333.
Right.
So that's 1 over 3, comma. Now we can work out our variance. Now our variance can be P 1 over 3 times Q. Q is 2 over 3 divided by N. N is 450. So work that out. 1 over 3 times 2 over 3 divided by 450. So we get, that's how we get 1 over 2025. That's our variance. So I'll leave it at that, 1 over 2025. That's our variance.
Right.
So now that we have our variance, right? Now that we have our variance, we're good, because now we can tell them, say, all right, write down this part now. Remember, it's bar X plus or minus Z alpha over 2. So we're using, remember, we're using proportion. So it's not bar anymore. It's our proportion. So it's P hat now. It's P hat. We're using our proportion. So proportion, it's going to be P hat in bracket or Z alpha over 2 in bracket. The formula now is the square root of PQ over N. So in that case, it's going to be 1/3 plus or minus, we work that out now, 1.96 in bracket. We just need to work out the square root of 1 over 2025. (1.96) in bracket the square root of 1 over
So 0.22.
0.32.
You mean the square root of 1 over 2025?
0. How much you got?
0.022.
And then you multiply it by 1.96.
(0.043).
Good. 0.0435555, whatever. So in that case now, our interval, just to swinge it here, is 1 over 3 plus or minus 0.0435555, or we can just put 6. So remember, 1 over 3 is 0.33. So in other words, it is 0.33 minus this is how much? 0. You can just put in the calculator 1 over 3 minus 0.0436.
0.2894.
Good. 0.2894. 3 decimal places fine. So then we'll add it now to it. Let me see, 0.33 plus this, 0.37 something. 37 what?
0. Hold on. (0.376).
0.376. That's it. All right. All right. 0.376, and that's that. Now, the next thing is they're gonna, now look how they're wicked. This topic is taught in where? This topic is taught in the last thing. Yet still they ask for margin of error.
Margin of error.
How can they do that? So no, that is so unfair. So now we are, so right here, when they said put in the critical values, these were the critical values. The critical values were our p hat, what's the critical value? P hat and our z alpha over 2, right? So you'd have to tell them, write both the letter and the value corresponding to this interval. What they really just wanted was p hat is 1 over 3. The next critical value they wanted was our z alpha over 2, which was the 1.96, right? Now, when you actually substitute the values and do the calculations, this is what we actually do right here. We did 2 and 3, we actually plugged in. But now, we also write out the formula right here. So we literally did all of the calculations for C and B here, but they just wanted us to write both the letter up here. So right here, so A and B was to just write down the Z and the P hat, but then down the bottom was to do the calculation. Now, margin of error. Margin of error now pretty much is just going to be, this is how we find the margin of error. It's just your highest value minus your lowest value when it is proportion. Highest value minus your lowest value for proportion give you margin of error. And that's all for the margin. So all we're going to do is work out 0.376 minus 0.289. Because look how the range wide. The range wide, man. So that must have some error in it. So that's our error. Work that out, and we get a very slim error. What's that working out to be?
0.376 minus
0.3765. 0.3765. No, I forgot. It's divided by, no, this is not right. This is saying 37.5%. The error
Isn't
would
it
be that.
0.087?
No, this too high. No, that's not it. Sorry about that. The proportions is what throw me off. I don't normally say margin of error with proportions, but typically when they say margin of error, remember the significance level. So if we're 95% confident, then the margin of error is 100 minus 95.
Which is
So
5%.
so the margin of error is 5%. But it's weird seeing it with a proportion. Usually they don't give you with a proportion because proportion tend to have less relative margin of error. But they gave us with a proportion question. So when they're making up these questions, I don't think it's well thought out. Don't think it's that thought out, but it's good. That's fine with us. That's fine. So that's our margin of error. Pull it that?
Yep.
All right, so right here, so write the lower limit. Literally, we did that already. So our lower limit, all I want us to do is put it right there, the 0.28. And write the upper limit, 0.376.
Mm-hmm.
And that was it. Yep, that's it. Everything else is hypothesis testing going forward. Because you notice how hypothesis testing important, because the reason why it's so important now is because everything that we did can come in hypothesis testing. Let me say it one more time. Every topic that we did now can come in hypothesis testing. So next week gonna be the most important week. All right?
Mm-hmm.
So next week we're gonna do null hypothesis and hypothesis testing. So that's pretty much it for today. Only thing I'm going to do is send you this recording, and also I have the papers from last year. I'll send it to you. Maybe you can look through to see if you see any questions from this particular topic that we did today. You can do them, but otherwise I don't have any more questions to add on to these.
Okay.
Yeah, so I'll just send you the last year paper, and you can navigate through it and look through and do those questions. All right?
Yeah, man.
All right, but I'll do it in the morning, of course. I'll send the paper and recording.
All
Right.
I know.
All right.
All right.
So take care. All right, take care, Charmaine. Have a good night.
Thanks.
All right.
Bye-bye.